Well, hi everyone. It's so nice to be with you today. I wish we could be in person, of course, but here we are again, back online and trying to do the best we can. So here we go. This week we're going to be looking at a few different statistical and modeling techniques that I used from my research that I did between 2012 and 2017 during my PhD at Colorado State. And I had you read one of my publications, and we'll take a look at that and talk about it in more detail. So today we'll be discussing oil and gas extraction, which was the focus of my research, and the produced water that's generated from oil and gas extraction. We'll talk a little bit about the chemical composition of produced water, my area of interest, which was Weld County, and then the methodology that I used for this particular publication, which heavily relied on data mining, regulatory agency data to identify risks for produced water spills and groundwater contamination. This research was published in the Environmental Science and Pollution Research Journal in, 2017. This was my third publication for my PhD research. So we'll talk a little bit about the paper and the quantitative techniques that I used in the paper. We're going to dive in more specifically to Mann-Whitney tests and to logistic regression. And then we'll go through some conclusions and next steps for my research. Before that, I want to take a quick look at our calendar and due dates. So as you can see, we're in week 13 and we're doing logistic regression. So you have a reading assignment that's due that will be reading that 2017 publication, and it will be due on April 17th, this Friday at 11:59 p.m. And from here on out, for the next 3 weeks, you will have a reading summary due every Friday. So you have one due this Friday, and then next week you will get a lecture from Gemma on principal component analysis, and then you'll have a reading summary due for that topic on April 24th at 11:59 p.m. And then the following week, we will have our guest lecturer, Dr. Jocelyn Lavallee, and she will cover a modeling introduction. And that will be our final reading summary that will be due, and that'll be May 1st at 11:59 p.m. The summaries I'd like you to submit will be half-page, single-space. You can submit that in the text box directly on the assignment in Canvas. You don't need to create a PDF and submit it that way. And these 3 readings will be graded as credit, no credit. So all you have to do is submit them. Please submit them on time. It's a complicated process for us to open up grading again if you submit late and we try to get the grades in that way. I, of course, want to be sensitive to your needs right now. It's this crazy time. And so, I'm still trying to work with you. Okay, so let's dive into this research. So the overall goal of my PhD research was to understand the effects of produced water spills on a soil, plant, and groundwater system, and to be able to make recommendations to reduce the risk for groundwater contamination at produced water spill sites. Produced water is generated from oil and gas extraction through vertical and horizontal drilling. And so this is a diagram showing the underground soil profile for oil and gas extraction utilizing hydraulic fracturing and horizontal drilling. So you can see there's the entrance site at the top of, on the land surface here, and a well is dug into a shale or sandstone formation. And then most often it drills out horizontally. That's this horizontal drilling we've been talking about. And about 1 million gallons of water are pumped into this well under high pressure with some chemical additives. And this high pressure fractures the shale. Natural gas and oil are released from the shale or sandstone formation, and this is mobilized, and the pressure is released, so it rushes back up to the wellhead. And so along with that oil and gas comes the water that was originally put down into the formation, as well as naturally occurring water that was in that shale formation. So this complex slurry of water is known as produced water. It comes back up to the wellhead surface, and this is a long-term event. Water will be produced from these wells for many years to come after the fracking event. And so what do they do with this water? Well, much of this water can be temporarily stored in these retainment ponds. And so you could see that this is more of like a North Dakota looking structure for a retainment pond. You don't often see this too much in Colorado. And so you'll see they have the fresh water on the right, and that's because the initial fracking process, it works better, it's more efficient if you have clean, fresh water. You can reuse water. That's technology that is being pursued in the oil and gas sector. But most oftentimes it's fresh water. So you have your fresh water here, and then you also have your produced water, which is a mixture of that water that was put down into the formation and water that is coming up from the formation. And much of the water is stored in these storage tanks. These are all connected tank. It's called a tank battery. They're all connected. And a lot of the water is transported through underground flow and pipelines. And I'll lastly say is that, with all this water that's produced, much of it is re-injected back into a well that is no longer producing water. So a well that had been fractured, it produced water for many years, now it's not producing anymore, and so you could put water back down and store it there. Not saying whether or not that's a good technique or not, but that is the main way produced water is dealt with. And so there are a lot of chemical constituents, organic and inorganic, that are in produced water. In my research, I studied BTEX, which is a group of aromatic hydrocarbons. That includes benzene, toluene, ethylbenzene, and xylene. Benzene and toluene are a particularly nasty group of organics. They are neurotoxins, they're carcinogens, so they cause cancer. And they actually they have a really rapid degradation rate. So that's one benefit of, these contaminants in the environment, is that they're not very persistent. They can rapidly degrade. And naphthalene has a longer degradation rate, so it takes longer to break down. And then produced water also contains high levels of salt, usually above that levels in seawater. And so these are all things that are naturally occurring within the water that's in the fracked formation. When I say formation, I mean a sandstone or shale formation. So these are naturally occurring constituents that are in that water and in that basin. So I was interested in looking at Weld County, Colorado, which is where the majority of fracking happens in our state and where the majority of natural gas is produced. So when we look at a map of Weld County, the majority of the area is ranch land and grasslands. You can see to the west, pretty near to Fort Collins, that in red, that's Greeley. So, that's the main urban area in Weld County. And Weld County has experienced rapid population growth, 28% from 1950 to now. And in 2016, there were 285,000 residents. And it's an interesting place because it has a transitioning economy, moving away from agribusiness to more focused on oil and gas extraction. So currently there are about 3,500 farms in Weld County and a 94% increase in oil and gas employees from 2009 to 2016. So we're really seeing a transition in this area. And Weld County relies on a variety of water sources: the Big Thompson, the Poudre River, the South Platte, and St. Vrain all run supply water for Weld County. But 25% of their water needs are met from underground aquifers. And so when you're thinking about spills of produced water, it's important to ask questions about how this spill is affecting groundwater, because a lot of that groundwater could be going to the public. Okay, so here's another map of Weld County. Let's see, in Colorado in general, back in 2013, 183 trillion barrels of produced water were generated. And so, you know, as I said, some of that water is reused. Some of that water is re-injected into these Class 2 injection wells, where they're put back into a fracked shale or sandstone formation. But a fraction of produced water gets spilled on the surface of the land during transport or during the fracking process itself. And so this leads to the question, well, where are these fracking locations and where are spills occurring? So currently we have 23,000 active wells. And back when I was doing my research in 2017, this was in, let's see, I think it was July of 2017. Just by then, there were 1,000 new drilling permits during this time. So, you know, there's been some pretty robust growth in the oil and gas industry. And you could see that the majority of our well locations are in the southwest portion of Weld County. And so within this study, I used a variety of quantitative concepts that you should have read about in this publication. So I data mined. I used publicly available data to, I used publicly available records to extract data to ask a variety of questions about produced water and risk for groundwater contamination. I utilized coding. I made multiple conversions and generated equations. I utilized log scale when I had non-normal data. I did tests for differences in medians. That's the Mann-Whitney U test, and I'm going to be talking about that today. I also utilized a test for evaluating differences in distribution, which is a word that I'm not going to try to say out loud right now, but you see that there. I used linear regression, very standard technique. I also used a pretty interesting technique called logistic regression, which we're going to talk about today, and in what circumstances you would use that type of regression. And then lastly, I used model comparison with AIC. And I know that Peter talked about that a little bit last week. And so it just helps you find the model that is, it helps you find the best model for your situation that explains the most. So here is a copy of a Form 19 with the Colorado Oil and Gas Conservation Commission. So if an oil and gas regulator, or excuse me, if an oil and gas producer has a spill, any type of spill from their extraction process, it could be drilling mud, produced water, oil, gas, these sorts of things, they have to fill out a Form 19 if they spill over 1 barrel, which is 42 gallons. And so these sorts of forms are fully available on the Colorado Oil and Gas Conservation Commission's website. Just for quickness, I'll call that COGCC. That's their acronym. And even though it's readily available and it has a wealth of information found here, it's really not in a very good usable format to try to do any data analysis, of course. So what I did was I first went and looked at these forms to see what kind of information do they provide. So I'll just point out a few different things here. So in this, you can see they say how many barrels are spilled and what type of material is spilled. And they also say if any barrels were recovered. In this example, it was oil, and they do not know how many barrels were spilled. And that's often because, you know, there's really not enough regulators to check on each of these 23,000 wells. So spills can happen and they can go on for quite a long time before anyone notices. So this can be a fairly inaccurate measure of how many barrels were spilled. And then it also shows, and this is kind of the crux of the research I'll be talking with you about today, it also shows the type of media that's impacted. And so for impacted media, they give the options of soil, groundwater, surface water, or a dry drainage feature. And so from my evaluation, most often I would see soil or groundwater that was affected, and that's what I studied with this research. I focused on soil and groundwater. And when they say impacted media, what that means is that they've tested and that the levels of contamination, usually for benzene or naphthalene or toluene or phenol, are higher than an EPA allowable standard. And so that's what it means to have impacted media. So you can see this is a sort of a binary response variable. You're saying soil is or is not contaminated. Groundwater is or is not contaminated. Okay, then you'll also notice that it says that the surface area impacted. So it gives you the length in feet and the width of the surface area that's been affected. And then they tell you have some information about the type of soil. And then kind of near the bottom, you see it says depth to groundwater. So when they discover that there is some sort of spill, they check the groundwater depth at that moment. So this is in feet, so it's saying 50 feet below the surface is where the water table lies. And there's additional information to this. There's remediation forms. There's all kinds of, you know, there are a variety of forms that go along with each individual spill. And so I spent a lovely summer going through every single spill and release report from 2015 in Weld County. And here is a spreadsheet of just some of the data I collected. And so you could see here I have soil and GW, that stands for groundwater. So this is saying if groundwater was or was not affected. And so 1 means yes, groundwater was affected. 0 means that no, it was not affected. And then we have the total surface area, the volume, the area, the depth to groundwater, as well as the company responsible for the spill. And then the spill type, and this is a type of coding I use because spills often, they're not just of one type of material. They'll say, oh, we spilled produced water, and we spilled oil, and we spilled drilling mud all together. So this is a sort of coding system that allows me to ask questions about, you know, the different constituents of spills. Excuse me. Okay, and so there was a study, a previous study that looked at some of these sorts of variables. That it was conducted by Gross et al. In 2013, or that's when it was published. And so I compared some of the summary statistics to the summary statistics they had calculated about oil and gas in Weld County back from, I think it was 2011. And so, yeah, so what we found was that in 2015, oil and gas related spills, and more specifically produced water spills, occurred more frequently, and they typically released a larger volume of waste as compared to the results from the 2011 study by Gross et al. So these are becoming more impactful on the landscape. And then when I looked at the different composition of all of the types of materials spilled at sites, anything that was a spill that contained produced water, I labeled these as produced water related spills. So produced water was included within this spill. And so you could see all of the different types of materials spilled, and on the x-axis and on the y-axis, we have the number of spills. And so you could see about 40% of spills were comprised of produced water related materials. So, you know, just shy of half is related to produced water. And so remember I said that a barrel of produced water is 42 gallons. So about 7,500 total barrels were reported to be spilled in Weld County during 2015, which equates to about half of an Olympic-sized swimming pool. Whew, that's quite a lot. And there was a wide range of barrels spilled at sites. So it ranged from half a barrel to just shy of 4,000 barrels. But the median spill size was 5 barrels, so tending towards the lower end of the numbers. And so there were some extraordinary spills that occurred during this year, and usually you have a few of those every year. And so when I looked at when soil was contaminated at a spill site and when groundwater was contaminated at a spill site, I found that out of all spill sites, about 90% of those resulted in soil contamination. And 32% of those resulted in groundwater contamination. So you can expect that out of all of your spills, about a third of them will result in groundwater contamination. And comparing back to that other study, I found that there were 25 additional oil and gas related spills with affected groundwater compared to the 1 year period during 2011 by Gross et al. And so there had been 54 produced water spills in 2011, and then there were 63 in 2015. And that the average produced water volume spilled at a site had increased by 9 barrels. So there had, in 2011, 7 barrels on average were spilled at a site, and this increased to 16 barrels by 2015. So getting into more specifically this research, once I found out the type of data that was available from these oil and gas spill reports, I was able to generate a few hypotheses. So I said that areas experiencing a spill had higher odds of contamination, groundwater contamination, if larger volumes of waste was spilled, larger groundwater surface areas were affected, and the depth to groundwater was shallow. So I asked these questions individually, saying that there would be higher odds of groundwater contamination if the depth to groundwater was shallow, and that the odds of groundwater contamination was higher if larger volumes of waste were spilled. And then I also asked this question in conjunction: do all three of these variables influence your risk of groundwater contamination? And so here we're looking at box plots of sites that had groundwater contamination and sites that did not have groundwater contamination. So that's on the x-axis. And on the y-axis, you're seeing the depth to groundwater at spill sites in meters. And so just be aware that when we're on this axis, we're going from 0 to 75 meters. So 75 meters would mean that you're 75 meters below the ground surface. So a larger number means that you're deeper below the surface. And so when we take a look at these two box plots, I always like to make box plots of my data because it shows you the distribution of your data. It's another way to look at things in addition to a histogram, for example, which I'm going to show you in a few minutes. And so what you can notice off the bat is you see that areas that had produced water spills but did not result in groundwater contamination, they had a higher median depth to groundwater at these sites. And then the sites that did have groundwater contamination, they almost always had really shallow groundwater. So they had lower depths to groundwater at spill sites. And you can see those dots, those represent outliers. So, you know, there is some spread in this data, and this would lead me to believe that there's unequal variance. You can see that where the median bar is, that's the very center bar. The higher values spread out really far from the median, and then the lower values are much more compact. And then there's also differences between the not contaminated and contaminated sites. There's a much smaller distribution of depths to groundwater at contaminated sites versus sites that did not have groundwater contamination. And so you might be tempted to ask if there's a difference in means. And why shouldn't you do that in this case? I'm going to give you a second to think about that. Well, the reason is just what I had said. There's this unequal variance about the mean. And because of this, a standard test like a t-test or an ANOVA, we would not be meeting the assumptions to utilize that test. And so we would get results that did not represent the real world. So let's take a look at that data in a different way. So this is changing that data into a histogram. So now you can see on the x-axis, we have our depth to groundwater in meters. And so larger numbers mean that you're going further down into your soil profile. And smaller numbers mean more shallow groundwater levels. And the graph that's on the top there, those are sites without contaminated groundwater. And then the graph that's on the lower portion there, that's sites with contaminated groundwater. I want you to notice that the x-axes, they have different scales here. I mean, the sites without contaminated groundwater go from 0 to 140. And that's because, you know, as we saw in those box plots, there was a much larger range of values observed at sites that did not have groundwater contamination. So let's take a look at that one first, the sites without groundwater contamination. What you can see is that I've mapped out on here the mean and the median. And the mean is in red and the median is in blue. So if we were to conduct an ANOVA, that would be looking at the mean. But you could see that the mean is being pushed over to deeper depths of groundwater because there's a skew in this data. It's right-tailed skew. And so the median is actually a better measure in this circumstance because we have skewed data and we have unequal variance about the mean. And we see the same pattern on the lower graph at sites that had groundwater contamination. It's not as stark in this one. The mean and the median are much nearer to each other. And so, and that's because the majority of sites that resulted in groundwater contamination had relatively shallow groundwater levels. And so you could see these two match up a little better. This histogram looks a little more normal than the sites without groundwater contamination. But now we want to compare the two, and they're very different. The scales are different for both. They're both skewed, and they have different distributions compared to one another. So this would lead you to want to choose a Mann-Whitney U test. The Mann-Whitney U test is also known as the Wilcoxon ranked sum test, but you need to be careful here because Wilcoxon ranked sum test, that can mean two different tests. So I always try to refer to it as the Mann-Whitney U test, which only means one thing. And it's a way of ranking your values, and when you're ranking, that's similar to how you would calculate a median, and so it's different from calculating a mean. And it allows you to compare between two independent groups. So for our circumstance, the two independent groups, we're comparing our sites that have groundwater contamination versus sites that do not have groundwater contamination. And the dependent variable needs to be ordinal or continuous. In our circumstance, our dependent variable is the depth to groundwater, and that's a continuous variable. But the data is not normally distributed. And that's why mainly you would utilize this test. It's a non-parametric test, meaning that the data is not normally distributed, and it doesn't need to be normally distributed for this test. It's a good test for small sample sizes. That's not the circumstance for this particular research question that I was asking, but it is good for small sample sizes. You do it for 2 samples, so it's similar to a t-test or an ANOVA with 2 samples. And it's used to test for differences in medians, which differentiates it from a t-test. And it tests whether 2 samples are likely to derive from the same population, i.e. that 2 populations have the same shape. And it's created for when your data is skewed or you have unequal variance about the mean, as we saw in the last slide, and your distribution does not follow any sort of typical distribution like a normal or student's distribution. And like all of these tests, there are assumptions, and so you could probably guess that this will be on the final. So the assumptions for the Mann-Whitney U test are that the dependent variable should be measured on an ordinal or continuous scale. And as I said, our dependent variable is the depth to groundwater. We're trying to find out what the median of depth to groundwater is when you have sites that did have groundwater contamination or didn't. And the independent variable should be 2 independent categorical groups. And so we have 2 categorical groups, contaminated or not contaminated. Observations should be independent, meaning that there should be no relationship between the 2 groups or within each group, so there's no ties. And observations are not normally distributed. However, they should follow the same shape, so they should both either be bell-shaped or they're both skewed to the left or skewed to the right. And in our circumstance, it's skewed to the right. Okay, so now we're asking if the likelihood of groundwater being contaminated with, if we can predict, so now we want to test whether or not the medians for the median for the depth to groundwater at sites are different for areas that had groundwater contamination and did not have groundwater contamination. And here's just a reminder, this is how the distribution of our data looks in these box plots. And so let's begin to do our Mann-Whitney U test. The way we do that is with on the spreadsheet, in the spreadsheet on the right, you can see in the very left column, we have coded data for whether contamination did or did not occur. And so one, it's been coded with a 1 if there was contamination. Ooh, sorry for that, that spelling error right there. And then 2, if there was no contamination. So you could see this is just the first 10 data points in my data set that I collected. So this is real data, but it's shortened, okay? So we're only working with 10 data points for this example, but there were actually something like 180 data points within this. So we had a good sample size. And so in the second column, you can see we have, it's called gw.depth.m. So that just means the depth to groundwater in meters at sites that had a produced water spill. And then on the very right is the ranking. And this is where the researcher comes in to do the statistical test. So what you do is you would order all of your depths to groundwater. This is, as you recall, this is your dependent variable, the depth to groundwater that we're studying. So I sorted this column from lowest to highest. So you could see, oops, sorry, in the lowest value for depth to groundwater in this study was 1.5 meters below the surface. And then the largest depth to groundwater within the shortened data was 6.10 meters below the surface. And so we have these in order. And what we do is we go ahead to our ranking column and we start giving it a ranked number. So my lowest number, 1.52, gets a ranking of 1. Then my second lowest number gets a ranking of 2. And then my third lowest number of 2.13 gets a ranking of 3, and so on. And you would do this for all of your numbers until you got to the end of your data set. And one thing I need to point out here is something called ties. So you could see that, you know, we have this in the middle column, we have a value of 3.05 meters twice in a row. And so how would you rank that? Well, you would actually, so I see a mistake here, I'm sorry. So, so the next number that would have gone for the first 3.05 would be the number 4. And then the second ranking number would be number 5. And so you would just take the average of those two. So rather than 4, you would put 4.5. And then here, I'm sorry, I made a mistake. Rather than this number 5 ranking, it would be 4.5. So they would both have that averaged ranking to get rid of the ties. You can see I did that correctly below. So we have a number of 3.66, and then we also then have a number of 3.66. So we have a tie in this data. So how do we change that rank? Well, the next number that would have gone here would have been 6. And then the following one would have been a ranking of 7. So we averaged the two, that's 6.5. And so it's given a rank of 6.5 and then another rank of 6.5. And then you carry on. So now you move to 8 and then 9 and 10. So your rankings will end with the same number of data points that you have in your data set. Okay, so next what you do, it's the bottom left here. You add up the ranks for both groups. So let's just pretend I had given all of these the correct ranking. So let's look for group number 1. Group number 1 is for sites that had contamination. So I've circled here for you in this spreadsheet all of the different data points that had resulted in contamination. And I'm going to add up those rankings. So for this lower value here, it had a ranking of 1. And then the next time there was groundwater contamination, it had a ranking of 5. And then the final time in this data set that there was groundwater contamination, it had a ranking of 9. So if we go back to the numbers in the lower left-hand corner, you could see for group 1, I've added up 1, 5, and 9. So I get a ranking for group 1 of 15. Now let's do that for number 2. So if I add up all of the different rankings that I found for groups with no contamination, I get the ranks 2, 3, 4, 6.5, 6.5, 8, and 10. And I add all of those numbers up and I get a ranking for group 2 of 40. The next thing you need to know is you need to know how many observations there are in each group. And so for my group number 1 with contamination, we had 3 observations. And then for my group 2 with no contamination, we had 7 observations. So carrying that data forward, you can see on the upper left-hand corner, we have our rankings and we have the different N values in each of our groups. And so now what we need to do is create our test statistic for the Mann-Whitney U test. And that's denoted as U, and it's the smaller of the U calculated for group 1 and a U calculated for group 2. And so you can see here are the equations to make those calculations. For U1, and they follow the same formats just for each group. So for U1, you would multiply the number of observations in group 1 times the number of observations in group 2 and add that to the number of observations in group 1 times the number of observations in group 1 plus 1 divided by 2, and then subtract the ranking of group 1. Okay, so that's a lot of words, but let's look at the numbers that we calculated. We have 3 times 7 because those are the values of N in each group. And we add that to the number 7, which is the N in group number 2, times number 7, which is the N in number 2, plus 1, divided by 2, and then you subtract that by 40, which was the ranking for group 2. And so you calculate the U1 and U2, and then to decide which value to use as your test statistic, you find the lower of either U1 or U2. So in our case, U1 equals 12, U2 equals 9. So 9 is our test statistic value that we are going to compare our critical value to. What you do is your test statistic, if it's larger than a U critical value that you would obtain from a table, you would accept the null hypothesis, and that would mean that you did not observe a statistically significant difference in medians between groups that had groundwater contamination and groups that had no contamination. But if your U statistic is smaller than your U critical value that you get from the table, you would reject the null hypothesis, meaning that there is a difference in means of groundwater depth between sites that had groundwater contamination and sites that did not have groundwater contamination. So now let's go to our table and look at find the U critical value so that we can compare that to our test statistic. So on the, in the column on the left side, you see N1. And so that is the number of observations that are in our first group, which was contamination. So that number is 3. And then on the top row, those are the numbers for the amount of observations in group N2, which was 7. So if you go from 3 and 7 and you connect the two, you see that the critical value is 1. So the critical value for this test, which had 10 total observations, 3 in group 1, 7 in group 2, that makes a critical value of 1. And for our U test statistic that we calculated the number 9. So 9 is larger than 1, meaning that we would accept the null hypothesis. There is no difference between the ranks or medians from the two samples. And so one thing I want you to be careful of is how the null hypothesis and comparison of the U test statistic to the U critical value, this is a little different than we've seen before. So to reject the null and accept the alternative hypothesis, your calculated U test statistic needs to be smaller than the critical value. And if you recall when we were looking at ANOVAs, for example, you wanted to find a value on the F distribution that was larger than your F critical value. And so in this circumstance, it's the opposite. And you're going to need to remember that for your final, that the way you reject the null hypothesis and accept the alternative hypothesis is in a Mann-Whitney U test is that the U test statistic needs to be smaller than the U critical value that you get from the table, okay? And so one thing I want to point out is that in the research article that you read, there really was a difference in means. The Mann-Whitney U test, I rejected the null hypothesis and I accepted the alternative hypothesis, that there was a difference in groundwater depth medians between sites that had groundwater contamination and sites that didn't have groundwater contamination. And the reason for that is because I was showing this abridged data that only had 10 observations. And so when you have those 10 observations, your critical value is very low, as you see. And so I had about 180 observations. It gives you a much larger U critical value by which to compare your calculated U test statistic. So yeah, in the actual research, I did find there was a difference in medians. And so I would like you to practice making these calculations. They will be on the final. They're fairly simplistic. Just make sure that you know how to mainly use this, the U1 and U2 calculation, and then how to decide which one to use as your U test statistic. It's always going to be that smaller value that you calculate. Okay, and another thing I recommend to do is sometimes if you put this whole thing in Excel, it can give you the wrong number if you're not careful with your parentheses. So I just recommend calculating this by hand and writing it all out so you know that you're taking the correct step at the correct time. When you do this in R, here are the results. And you remember I said that Mann-Whitney U test is also called a Wilcoxon ranked sum test. And so in R, they call it this Wilcox test. And it does the same thing. So it's not giving you the critical value or your U test statistic, but it is giving you a p-value. And the p-value is below our alpha of 0.05. And that's when we would reject the null hypothesis and accept the alternative hypothesis that there is a difference in the median depth to groundwater at sites that have and do not have groundwater contamination. So these are the actual results. And so this is, on the midterm, this is all I would ask you to do. I would ask you to be able to look at this result, look at the p-value, and to tell me whether or not there is a difference in medians or a statistical difference in medians, or if there is not.